In this video, we're going to look at some properties of sequences. We say the sequence an is increasing if an plus 1 is larger than an. That means every successive term is larger than the previous term. So you can see 2 is bigger than 1, 4 is bigger than 2, 8 is bigger than 4, 16 is bigger than 8. And likewise, we say a sequence an is decreasing if every successive term is less than the previous term. So we have 25 is less than 125, 5 is less than 25, and it becomes progressively smaller in magnitude. And we say a sequence is monotonic if it's either increasing or decreasing. We say a sequence an is bounded above if an is less than or equal to m for all n. So you can think of m as an upper bound for the sequence. We say the sequence an is bounded below if an is larger or equal to L for all n. So you can think of L as a lower bound for the sequence. And we say the sequence an is alternating if the product of successive terms is negative. So we have 1, negative 1/2. You can see the product of these two terms is negative. The product of negative 1 over 8 times 1 over 16 is a negative number. The general term of an alternating sequence usually looks like this. Negative 1 to the n times something. The reason for that is negative 1 to the n creates a plus or minus. When we raise negative 1 to an even integer, we get plus 1. When negative 1 is raised to an odd integer, we get negative 1. So we get basically plus, minus, plus, minus, plus, minus, or negative plus, negative plus, negative plus, alternating terms. All right, we say a sequence an is bounded above and monotonically increasing, then the sequence an converges. And similarly, if a sequence is monotonically decreasing and bounded below, then a sequence an converges. Therefore, every bounded monotonic sequence converges. So let's look at two sequences. We have an is equal to 2 plus 1 over n, bn is equal to 2 minus 1 over n goes from 1 to 3 all the way to infinity. And we would like to prove that these two sequences, an and bn, are bounded and monotonic, and we would also like to prove that both of these sequences converge to 2. All right, so for the first sequence, we have an is equal to 2 plus 1 over n goes from 1 to infinity. And it's always a good idea to write a few terms of the sequence to get a feel of what this sequence is doing. Put n equals 1, 2 plus 1, we get 3. N equals 2, we get 5 over 2. N equals 3, we get 7 divided by 3. N equals 4, we get 9 divided by 4. And plug n equals 10, we get 21 divided by 10. And so on. Clearly, the sequence an is bounded above by 3. Because it starts off at 3 and it starts decreasing. Bounded above by 3. So we say an is less than or equal to 3 for all n. That means 3 is an upper bound for the sequence. Now, let's find a lower bound. So to find a lower bound, let's take the limit as n goes to infinity of 2 plus 1 over n. That's a general term of a sequence. 1 over n approaches 0 as n goes to infinity, so the result is 2. This is a lower bound. So clearly we can see that an is larger than 2 for all n. That means the general term an is less than or equal to 3 and larger than 2. So it has an upper bound, which is 3. It has a lower bound, which is 2. So we can say absolute value of an is less than or equal to 3 for n larger or equal to 1. That means the sequence an is a bounded sequence. So this is a bounded sequence. Now let's show that it's monotonically decreasing. Well, intuitively we can see that the terms of this sequence are decreasing. We have 3 here and 2.5, 7 over 3, 9 over 4. The 10th term is 21 over 10, which is 2.1. Clearly it's decreasing. But oftentimes in math we have to prove something is decreasing. We can't just say it's decreasing. So let's do that. We can look at a derivative, f of x is equal to 2 plus 1 over x. Let's take the derivative and prove that the derivative is negative and hence the function is decreasing. So we're basically using the stuff we learned in calculus for a function of x. So f prime of x, differentiate, derivative of 2 is 0, and derivative of 1 over x is negative 1 over x squared. The derivative is negative for all x. So what does that tell us? That means that f of x is decreasing. Well, of course, that means f of n, the sequence, is decreasing for all x. So we have applied a derivative to show that this sequence is decreasing. So basically, we have a sequence that's bounded. So bounded. And it's also monotonically decreasing. Bounded plus monotonic. Therefore, we know this sequence converges. But what does it converge to? So to do that, we just take the limit as n goes to infinity. Limit n goes to infinity of an is equal to limit as n goes to infinity of 2 plus 1 over n is equal to 2 because 1 over n approaches 0 as n goes to infinity. So we say the sequence an converges. It converges to 2. Now, let's look at the other sequence. The other sequence is very similar in structure. It just has a negative in between 2 and 1 over n. So the sequence Bn, n goes from 1 to infinity. This is equal to 2 minus 1 over n. N goes from 1 to infinity. Let's list a few terms. N equals 1, we get 1. N equals 2, we get 3 half. N equals 3, we get 5 thirds. N equals 4, we get 7 over 4. N equals 10, we get 19 over 10, and so on. So clearly the sequence, Bn, is bounded above. Is bounded above by 2. How do we know that? Well, let's take the limit. We can see it's increasing, and it seems to be approaching a number, the number 2, because the 10th term is 19 over 10. So let's take the limit as n goes to infinity of 2 minus 1 over n, and 1 over n approaches 0 as n goes to infinity, so the result is 2. So clearly this sequence is bounded above by 2. That means Bn is less than 2 for all n. It's also bounded below by 1 because it starts at 1. So we can see that Bn is larger or equal to 1 for all n. So that means that Bn is bounded above by 2 and bounded below by 1. This is the upper bound 2, lower bound is 1. That means the absolute value of Bn is less than 2 for n, larger or equal to 1. That, of course, means the sequence Bn is bounded. It's a bounded sequence. But it's also monotonically increasing. How do we know that? Because the successive terms increase. We can, of course, take the derivative like we did for the previous term an, but we don't need to because we know how that works. If we did do that, you would set it up as f of x is equal to 2 plus 1 over x, and you would show that f prime of x is equal to, this is 2 minus 1 over x, 2 minus 1 over x, and you would show that f prime of x is equal to 1 over x squared, which is always positive. If the derivative is positive, the function is increasing, and hence the sequence is increasing. So that's how you would prove it if you wanted to. So what we basically have, we have a bounded sequence that is also monotonically increasing. Therefore, this sequence converges. But what does it converge to? We're of course going to take a limit to do that. So we have a bounded monotonic sequence and take the limit as n goes to infinity of Bn. This is equal to limit as n goes to infinity of 2 minus 1 over n, which is equal to 2. So we have a bounded plus monotonic sequence that converges, and this means the sequence converges, and we found that the value of the converging limit by taking a limit as n goes to infinity. This sequence converges to 2. Now let's look at the graph of these two sequences. So we have the two sequences. We have an here, and n goes from 1 to infinity, 2 plus 1 over n, and you can see this is a monotonically decreasing bounded sequence. It is progressively decreasing to the value of y equals 2. And this is, of course, a convergent sequence, and its converging limit is 2. In the green, we have Bn, which is a monotonically increasing bounded sequence. So you can see how it's increasing, and the terms are progressively getting larger until it reaches 2. It never really reaches there because y equals 2 is a horizontal asymptote, but the terms are getting closer and closer to the limiting value of 2. So both sequences are convergent. They both converge to 2. All right, thanks.